All right. Hello, everybody. Good morning. Welcome to week 5 of classes. There are, I believe, 16 weeks of classes. And so we're over a quarter done. We are going to be starting chapter 3 officially. We kind of started chapter 3 a little bit right before the exam. And we're going to be kind of diving in more. So we're going to be working under the module for week 5 and 6, under the module section, which is chapter 3, properties of pure substances. So you have a homework that is due next Friday that I will be posting soon. It will be on chapter 3 and what we go over. And I'm still grading the exams. I haven't finished yet. And are there any questions before we get started? Okay. Well, hopefully I gave everybody time to look up some of the definitions for the various vocab for this lesson. So I am assuming that you have all done that. If you find yourself kind of confused by some of the vocab that I'm using, please make sure to review on the course modules under the lesson for this week 5 and week 6. There are 2 PowerPoint PDFs that are some of the main concepts from this chapter, along with this Word document of definitions that you need to know. So these are the ones that I gave you last week. You should have looked them up. I gave you about 10 minutes at the end of class, and I'm going to be using those terms now. If you don't know them or you didn't do that, please make sure to do that as soon as you can. There's also the Friday problems that will work on Friday, and then your homework assignments that are here. I haven't opened the homework yet, so you can't click on this yet, but I'll do that later today. I will not be going over the exam. I'm still grading them, but also typically I don't go over the exams unless they're like specific grades so far. Noah, I've only graded question 1 and question 2, and question 1 was particularly easy, so I'm not sure if I can really give a good judgment on how the exams look so far. So were there any specific questions about the exam that anyone had? All right, well, I am recording today's lesson. I'll post it under this material here, and I'll post any notes from today here as well. So you can review it, or if you're really sleepy or don't feel well or something, you can watch it again later. All right. For chapter 3 has a lot of new information in it, and I would highly encourage you to keep up with the reading and keep up with the definitions, keep coming to class, work on problems yourself. There's a lot of new material in here, and this chapter, we continue to build on this chapter from here on out. So understanding this chapter will be really important. All right, so I'm going to get started with some notes. Ooh, meant to move this, not make it laying across there. All right. Then I have, trying to pull up the chat. Here we go. All right, so we are starting in chapter 3, which is properties of pure substances. This is, what's today? The 8th, I believe, February 8th. And this is following exam 1 and chapters 1 and 2. When we are looking at pure substances, we're looking at pure substances that exist in different forms. So I'm going to draw a little graph here where we have temperature on one scale and then specific volume on another axis, on the x-axis. And here we have diagram that kind of looks something like this. We have an increase, then a plateau, and then an increase. And we have multiple points on this line. We have point 1, point 2, point 3, point 4, and point 5. The book does a really nice job of going over this. I'm kind of just trying to condense it down in a way that makes sense to me. But if this is still confusing to you, please make sure to look in the book. So at point 1 here, this is what we consider to be a compressed liquid. Compressed liquid, which I'm going to abbreviate to CL in some of the problems we do later. Compressed liquid. So compressed liquid is generally pretty dependent on temperature. It occurs at a low temperature, and it's where you have an entire liquid, there's no vapor form, and it's kind of in a compressed form. This is a relatively rare type of phase that we look at, but they do have their own specific tables. We will look at it a little bit. So compressed liquids typically at low temperatures, and it's where you have this liquid that's kind of under some sort of pressure, or it's really constrained. There's no vapor, which is pretty rare. So compressed liquid. At point 2, we have saturated liquid. So this is where your liquid is about to vaporize, turn into a vapor, but you don't have any vapor yet. If you remember in the book, we use the subscript F for this. So I'm going to use this generic variable Y and then have this subscript F here. So this is denoting that saturated liquid has a subscript of F. So at point 3, here's where we have a saturated liquid vapor. So you have some liquid, some vapor. Saturated liquid vapor. And here I call this SLV. And this is where we have some general term Y. This could be your internal energy. It could be enthalpy. And then we have FG, sub F sub G as a subscript for a saturated liquid vapor. At point 4, we have our saturated vapor. So SV, and this has the subscript of G. Saturated vapor is, liquid. We know what liquid is. Vapor is when it's kind of vaporizing, going through a vaporization process, turning into something more like water vapor or a type of gas, which is where this sub G comes from. And you can see as temperature rises, if you have kind of a cold compressed liquid, it gets hotter, it's about to vaporize, you're about to boil water. For a little while, you have water and vapor that's boiling, and eventually all of it goes to vapor. And then if you keep heating that up, that vapor up, you get to 0.5, which is called a superheated vapor. Superheated vapor. SHV. So this is probably relatively simple to a lot of you, I'm hoping. Maybe some of you have started reading the chapter, you've already read about this, and it kind of makes sense, right? If you have kind of a cold liquid that's compressed in a container, you take it, you start to boil it, you're going to have these phase changes that occur. And when we're looking at the upcoming problems that we're going to look at, we're really concerned with what sort of pure substance we're looking at, what sort of condition it's in. And this determines what table you use. A lot of what we're going to be looking at is water or refrigerant R134A. So in the modules, you'll see that I have in the modules here, the introduction of pure substances and the calculating the properties of pure substances. These are two kind of helpful points from the chapter. They go over these different pure substance phases, starting with a subcooled or compressed liquid. I will always call this a compressed liquid, but it's also just a liquid at a subcooled temperature, a very cold temperature. So here you can see the blues kind of representing that it's cold. We're down at 20 degrees Celsius. There's no vapor that's in this whole system. This is all liquid water, and or just a liquid system. So at 1 atm and 20 degrees Celsius, water exists in the liquid phase. Then we can move over to point 2, which is saturated liquid. So water exists at a liquid that's ready to vaporize. Compressed liquid is not about to vaporize. It's not even close. There's no vapors that are even on the horizon. Saturated liquid means it's at that point 2. It's about to reach that plateau and start vaporizing. Typically it's at all the time it's at a higher temperature than a compressed liquid. So that's point 2. Then at point 3, we have our saturated liquid vapor, where some is liquid, some is vapor. We have some vapor here, some liquid here, some of the water. Liquid is vaporizing into water vapor. Then point 4 is saturated vapor. So all of the liquid water has been vaporized, but it's still close to that liquid vapor point. It hasn't fully become superheated. It's very close to that vaporization point with the liquid. If we continue to superheat and continue to apply heat up to 300 degrees Celsius, now we have 0.5, which is a superheated vapor. Are there any questions about this diagram, which I drew, or any of these different phases? Okay, so they're pretty straightforward, but this becomes a very important concept. So make sure that you understand each of these. So I'm going to keep going. All right, so we look at this a little bit different in the book as well, where they, instead of doing the straightforward diagram that kind of looks like this, for each liquid, you can kind of look at it this way as well, where we're starting with this compressed liquid vapor region here. We're coming up to our saturated liquid vapor region, our saturated vapor, and then our superheated vapor. But these are also dependent upon the pressure. So at different pressures, you can have a different line. So here's at pressure 1, here's at a higher pressure, some pressure 2. So this might be at 1 atm, this might be at 2 atm. So your line will shift. And all of these are also dependent upon a critical point. Critical point is one of your definitions. So a lot of this liquid and vapor are dependent and the superheated vapor are dependent upon the critical point of your substance. When I look over at the other document for your module, this is the pure substances chapter 3. I think it's called like calculating pure substances. This is kind of relating it back to when we first went over the appendices tables, the tables in the back of your book on page like 933. And we can look at, if we're looking for specific volume, internal energy, enthalpy, or entropy for a given substance, water or R134A refrigerant is what we're going to be looking at. We can look at the specific volume for a saturated liquid, the specific volume for a saturated vapor, the internal energy for a saturated liquid, the internal energy for a saturated vapor, or the internal energy for a liquid vapor region. So I'm going to come back to my whiteboard. So here we can see that if we have Y sub F, this is a saturated liquid. So it's all liquid about to turn into a vapor. If we have Y sub G, this could be internal energy, enthalpy, or specific volume or entropy. Y could be, I'm just using Y as a placeholder. This is our saturated liquid vapor. I'm sorry, this is our saturated vapor. Y sub G is our saturated vapor. And Y F sub Fg, this is our saturated liquid vapor. This is specific volume. So the equation for y sub fg is our y sub g term minus our y sub f term. So for some of your values, this is given. For some of them, you might need to calculate it. If we come back and look at the PowerPoint again, we can see here that we have our internal energy for a saturated vapor, our internal energy for saturated liquid. So our internal energy for a saturated liquid vapor should be this term minus this term. So 2,374.9 minus 0 is 2,374.9. 2,381.8 minus 21.019 is 2,360.8. So here this value is given. Sometimes, like with specific volume, it is not given. All right. So moving on. Oh, there's one thing I want to note. These tables have all been generated by scientists over the years, and these have been calculated in labs, and they are calculated based on the change from reference state. So all of these measurements are only changes from the reference state. So we can only measure when we have a comparison, right? So we have R134A at negative 40 degrees Celsius. Water, we have at 0.01 degrees Celsius. This is the reference state that we're using, and we're comparing everything to that. So these are comparative tables based on this reference state. All right. So I'm going to come back to the whiteboard and I'm going to clear this unless anybody needs more time writing. All right. So I want to talk a little bit more about saturated liquid vapors. Saturated liquid vapor, which is that plateau or 0.3. And when we're looking at saturated liquid vapor, part of it is liquid, part of it is vapor. That's kind of the definition. So you have some liquid that's vaporizing, you might have some vapor that's depositing. So one of the main concepts that we use when we look at saturated liquid vapor is the concept of quality, which is represented by the term X. And X is the ratio of mass of vapor to total mass. Mass of vapor to total mass. So this is saying X, our quality, is equal to the mass of our vapor over our total mass. So X is a ratio term, it's a unitless term, and it's going to be between 0 and 1. If you have a value of 1, your entire system is vapor. If you have a value of 0, your entire system is liquid. Because our total mass is just our mass of our liquid plus our mass of our vapor, which makes sense for a liquid vapor region. So the mass of our liquid plus the mass of our vapor is equal to our mass total. So this kind of logic where our total mass is equal to our mass of our liquid plus the mass of our vapor also applies to things like enthalpy. Our total enthalpy is the mass of our enthalpy and the mass of our vapor for saturated liquid vapors. But quality is only for are saturated liquid vapor. If you see the word quality, if you see an X, you know for sure it's saturated liquid vapor. It's not a compressed liquid. It's not a superheated vapor. It's not a saturated liquid. It is only a saturated liquid vapor. Okay. So we use X, we use quality. X can be used to calculate specific volume, pressure, temperature, and other parts of equations. X can be used to calculate specific volume, pressure, temperature, etc. So we'll see some examples of that later. But the way that we use it to calculate these different terms is through this equation. So in general, our Y variable, just some variable that's representing either internal energy, enthalpy, specific volume, entropy, whatever. Our Y term that's average, our average Y term, which is generally just going to be our Y term, is equal to our variable of our saturated liquid plus our quality times our variable of our saturated liquid vapor. So this equation we will use frequently. And remember that the X quality is representing the amount of vapor over the amount of total mass. So for instance, if we're not looking at Y, if we're looking at specific variables, if we have internal energy, then we have internal energy of a saturated liquid plus quality times internal energy of our saturated liquid vapor region. And this has units of kilojoules per kilogram. So this is the exact same equation. I'm just applying it to internal energy. We can also do that with enthalpy. Our average enthalpy value is going to be our enthalpy of our saturated liquid plus quality times our enthalpy of our saturated liquid vapor. Once again, units of kilojoules per unit mass because we're looking at specific values here. And we can also commonly do this for specific volume. Our average specific volume is going to be our specific volume of our fluid, our saturated liquid, plus quality times specific volume of our saturated liquid vapor region. And this has units of a volume per mass or a cubic meter per kilogram. Any questions?
X is the mass of vapor over the mass of total for every single one of those equations.
Yes. So this X is always going to be this quality term, which is our mass vapor over our mass total.
For the second equation on the right, the H average equals H of S plus X of U of G.
Nope,
Okay.
That's a mistake on my part. Sorry, I got carried away. It's still H here. This is all internal energy. This is all enthalpy. That's my mistake. This is all specific volume. So they'll all follow this exact same format. So if you remember, I'm going to go back to the slide here in a second, but if you remember, you can look up the internal energy value for your saturated liquid vapor region, U sub Fg, but you cannot look it up for specific volume. So here's where you're going to have to use that equation of specific volume of the saturated vapor minus specific volume of the saturated liquid is equal to specific volume of the saturated liquid vapor. Does anyone need more time writing? Okay, so what I was saying was here you can look up your specific volume, or I'm sorry, your internal energy for both your saturated liquid, your saturated vapor, and your saturated liquid vapor. But for specific volume, you have no saturated liquid vapor term. So here's where you're going to have to use the equation that I presented on the last whiteboard, which is specific volume of your saturated liquid vapor is this term minus this term. If you don't want to look it up, you can also just do the same for your internal energy, enthalpy, or entropy as well. Okay, so when we look at superheated vapor, this is typically where our entire liquid has been vaporized, it's continued to be heated, and now it's in a different phase called a superheated vapor. It's characterized by high temperatures, high specific volumes, lower pressures, and it is above this critical point of temperature. So here is where we have our saturated liquid vapor line here. We have saturated liquid vapor line, saturated vapor, and we have this term for our enthalpy of saturated vapor. And when our enthalpy of our superheated vapor or enthalpy of our system, so the heat content of our system goes above the heat content of this saturated vapor, so this enthalpy is greater than the enthalpy of our saturated vapor, above this critical point is where you get to superheated vapor. So your higher enthalpies, also higher internal energies, which we know enthalpy and internal energy are related by pressure and volume, which is why pressure and volume are also in here. And we know enthalpy is also related to temperature. So all of these kind of make sense, but we start to get saturated vapor becomes superheated vapor once we have higher levels of internal energy, higher levels of enthalpy than are on our saturated liquid vapor region. So I just wrote this down, but here's your quality term, your mass of your vapor over your mass total, where your mass total is your mass of your liquid plus your mass of your vapor. So quality is always between 0 and 1. It will be 0 if all of it is liquid. It will be 1 if all of it is a saturated vapor, which I just said. And here's kind of another way to visualize it. So you have some sort of saturated vapor, you have some sort of saturated liquid. You're looking at your overall system like this. And one way where you can look at either liquid or vapor is to use quality. And then the last slide here is what I went over again with these equations, where you can have, you can use quality to calculate your average specific volume, enthalpy, internal energy terms. So I just wrote these down. They're also in these slides here. It's explained in the book as well. So similar to superheated vapor, compressed liquid is where we kind of get away from this saturated liquid vapor region. We get at colder temperatures, or we get at way higher pressures. And this is where our, for any given pressure and temperature, here's where our specific volume, internal energy, or enthalpy are about equal to or lower than the internal energy, specific volume, or enthalpy of the saturated liquid at a given low temperature. So it's kind of close to this saturated liquid region, but typically we're at a lower temperature, possibly a smaller enthalpy, internal energy, or specific volume. All right. So I'm going to move now to doing an example problem to kind of start applying these. All right. So this is example 331. I think that's right. This is an example problem. I don't remember if it's 331 or not. That's what I had written down, but now I'm guessing that, second guessing that. All right, so we have a mass of 200 grams, of saturated liquid. Here I'm just going to write SL from now on, but for this time I'll write it so you have it. Saturated liquid, SL, is completely a mass of 200 grams of saturated liquid is completely vaporized at a constant pressure, is completely vaporized at a constant pressure. Does somebody have a question? Okay, I think somebody's not on mute, so just check yourself. Okay, at a constant pressure, oh, this should just say A, at a constant pressure of 100 kilopascal. A mass of 200 grams of saturated liquid is completely vaporized at a constant pressure of 100 kilopascal. We want to determine A, the change in volume, and B, energy transfer to the water. Energy transfer to the water. All right, so I'm going to give you a second to think about some of the equations I've presented, maybe how you think you're going to approach this problem. And for a lot of people, I know the hardest part is getting started. So I'm trying to work on that a little bit, try to figure out how you would get started. All right. So we are going to be using the tables in the back of the book, just to let you know. Okay. For a lot of
In the
these
exam, are you going to give us that table?
yes. So on the exam, I copy the part of the table that you'll need and provide it. But for the homeworks, I do not. Okay. So for all of these problems, the first thing that I do is I always start and I figure out if it's a compressed liquid, saturated liquid, a saturated liquid vapor, a saturated vapor, or a superheated vapor. Because compressed liquid is in compressed liquid, we use one set of information, and then for our saturated liquid vapor regions, we use tables A4 for water, and then superheated liquids, we use table A6. So these all have different tables that we're going to use. So that's why it's important to first figure out which one you're working with. So this one's pretty easy because it tells us in the problem statement what we have. So we know that we have a saturated liquid. So we know that we're going to be using table A4 or possibly table A5. So table A4 or A5. So I would open your books in the 8th edition. I'm on page 904 for table A4. So you should be close to there. In the 9th edition, I think it's a little bit later, but I have a teacher's copy. So maybe it's not, it might be a little bit earlier. Actually, it looks like it's on page 888. So if you look here for on page 904, table A4, your first row is temperature. And then on the next page, table A5, your first row is pressure. So it depends on if you're working with pressure or temperature, and if you're working with your saturation pressure or your saturation temperature. So table A4 works with saturation pressure. Table A5 works with saturation temperature. So here we're given information about pressure. We know that we have a constant pressure for the saturated liquid. So we're going to be working with table A5, which has pressure as our first row here that we're given, our first column. All right, so we're going to be working with table A5. And for part A, we are looking for change in volume. So the next thing that I always do is I check the tables. So I figure out what I'm working with, I figure out what table I'm probably going to use, and then I check the table. So when I look at table A5 and I look at pressure of 100 kilopascals, for part A, I know that I'm looking at volume related terms. So if I look at 100 kilopascal on page 906 and I look across, I can see that my specific volume of my saturated liquid is really small at 0.001043 cubic meter per kilogram. And then my saturated vapor term is going to be much larger at 1.6941 cubic meter per kilogram. And I want this total change in volume here that's occurring. So my total change in volume is going to be equal to well, okay, yeah. So I know that my total change in volume is going to be equal to my specific volume of my liquid vapor, saturated liquid vapor times a mass term. Because if you remember, our specific volume times mass is equal to volume. Volume over mass is equal to specific volume. And we have this saturated liquid that's being vaporized. So we have this liquid vapor region that's occurring. So we don't have entirely liquid or entirely vapor during that vaporization process. At the beginning, we have entirely liquid. At the end, we have entirely vapor. But during the process, we have this saturated liquid vapor. So we're interested in mass, which we're given, and then our specific volume of our saturated liquid vapor. If you remember, specific volume does not give you values for specific volume for saturated liquid vapor. So here's where you have to use that equation where specific volume of a liquid vapor region is equal to the specific volume of the vapor minus specific volume of the liquid, which is going to be 1.6941 minus 0.001043 cubic meter per kilogram, which gives us 1.6931 cubic meter per kilogram. So now we have everything that we need to solve for part A. So now we know 200 grams times 1.6931 cubic meter per kilogram. And we know we want to cancel the kilograms and grams. So we're going to need to convert these grams into kilograms. So we will need, 1 kilogram has 1,000 grams. So now we can get the grams to cancel, we can get the kilograms to cancel, and the term that we're left with is cubic meters, which is the volume term that we want. So this gives us 0.339 cubic meters is the change in volume for part A. Anyone need more time writing?
Yes, please.
Okay. Oh, it's not someone, it's my dog. He's over here snoring so loudly. Now he's gonna stop. Yeah, he does this during all of my recordings. He lays right next to me and snores really loudly. And I think it's partially fake and he just wants attention because I'm paying attention to you guys, not to him, and he gets jealous. So yeah. All right, so anybody else need more time writing? I will be posting these as well as a recording. All right, so now we have, I'm just gonna erase part of it so I can keep the second part. So now we figured out the specific volume and the change in volume in our liquid vapor region that's occurring. But now we wanna know our energy transfer to the water. So when we're looking at energy transfer to the water, energy transfer to the water is going to be occurring at a constant pressure. And so if this saturated liquid is being vaporized at a constant pressure, then we have a change in temperature that's occurring. And the term that's associated with the change in temperature or the change in heat content is typically going to be enthalpy. So on an exam, I would probably ask you like the enthalpy change or something that's a little more obvious, because energy, well, all of thermodynamics is energy. So are you using the energy equation? Are you using enthalpy, internal energy, anything? But for this one, we can make the assumption that we are heating up 200 grams of water at a constant pressure to vaporize it. So we can assume that we're adding heat content, we're having a change in heat content that's occurring. We will also have a change in internal energy, but that's not what's being transferred to the water. What's being transferred to the water is heat content. So here we're going to look at the energy transfer to the water, which is going to be enthalpy, which we know is heat content, or heat content like energy. And this is going to be mass times our specific enthalpy, and our enthalpy, our change in enthalpy that's occurring between the liquid.
Snore. So funny.
He snores so loud. Hey, Phoebe.
He was so fat too. He was my little doughboy. A cute little doughboy.
Yeah, okay. I woke him up, so maybe he'll stop snoring. Okay. You're a good boy. I know, you're a good boy. Thank you. All right. So all right, so we have this enthalpy change in our saturated liquid vapor region. And if we have specific enthalpy, which is what we're looking up in the table, if we multiply that by mass, we get this total energy that's occurring during this vaporization. So here, this one's even easier. Yeah, I agree. He's the best.
He reminded me of the guy off of Up, the old man when he's sleeping. That's what he reminded me of.
Probably. He is an old man. He
And when you wake him up, he would just roll. He had a very like barrel belly, right? So when you woke him up, he would like, and he just look at you like this was Paula, kind of, as he rolled on his side a little bit, and he'd look at you. And then he'd just fall back down and go to sleep. He was like these kids. He didn't get upset like my chihuahua would. My chihuahua would actually growl. He goes, he'd get like a really, like
okay,
a really.
I'm gonna keep going. I don't know if you know you're not on mute. Okay, so here we have our mass times our internal energy, and we can look up this internal energy term just in the back of the book. So once again, we're going to go to page 906, which is table A5, and we have our pressure of 100 kilopascals. We're going to look over and we're going to look at our enthalpy term and our enthalpy term for our specific liquid vapor. And this is 2000. So for our enthalpy term, 2257.5 kilojoules per kilogram. I just looked that up in the table. Our mass is given to us here as grams. Last time I did that unit conversion here, I'm just going to say, well, I know 200 grams is 0.2 kilograms. And then here we'll have kilograms cancel out. We have kilojoules, which is an energy term, which is what we want. And then we have this as 451.5 kilojoules is our enthalpy that's transferred to the water. So this is probably positive if we're saying our boiling water is our system and we're transferring energy in. We can also just say that it's transferred to the water. We know which way it's going. We know the direction that it's going. All right. As you can tell from these tables, you should probably know how to convert between Pascal and kilopascal and megapascal. Yeah, so the transfer would be going into the system, which is why it's positive. So into the water from the surroundings. You should also start to get really familiar with these tables, using these tables. Other questions? Okay, I'm gonna do another example. And then I'm gonna have you guys do an example and then we're done. All right, so here's another example, slightly different. Here we have a rigid tank. Rigid means that it's set volume, it's not gonna be moving volume. So a rigid tank contains 3 kilograms. A rigid tank contains 3 kilograms of water at 50 degrees Celsius. 3 kilograms of water at 50 degrees Celsius. If 1.2 kilograms of water is liquid, if 1.2 kilograms of water is liquid, and the rest is vapor, and the rest is vapor, determine pressure and volume of the tank. Determine pressure and volume of the tank. So a rigid tank contains 3 kilograms of water at 50 degrees Celsius. If 1.2 kilograms of water is liquid and the rest is vapor, determine pressure and volume of the tank. So the first step that we always do is this, no, 50 degrees C does not mean a compressed liquid. In fact, we have hints that this is not a compressed liquid because we know that part of it is vapor. In a compressed liquid, there's absolutely no vapor even about to occur, no vapor on the horizon. There's no vapor. So typically compressed liquid is like a lot colder temperature or a lot higher pressure. And we'll look at a few examples of that a little later. Probably not this class. But yeah, it's all the terminology is hard and like determining the classification, so no worries at all. All right, so the first step we always do is it's a compressed liquid, a saturated liquid vapor, a saturated vapor, or a superheated vapor. And for this problem, we know that some is liquid and some is vapor, so we know that it's a saturated liquid vapor. Yeah. So we know that it's a saturated liquid vapor, and there's also something here that jumps out to me. Part of it is liquid and we're given a mass, and part of it is vapor. I'm thinking we're gonna have to do something with quality. So just as a note, probably quality. I'm trying to help you figure out how to start problems and see where you're going, because I know some people are struggling with that. So if this note doesn't help you, don't include it. I'm just putting that for fun. All right, and then next, I always check the tables. So the table that I want to check this time, well, I know I have a saturated liquid vapor, so it's going to be table A4, A5, table A4, A5, because I know it's a water. If this was refrigerant, it would be a different set of tables, but for water and a saturated liquid vapor, I'm going to be looking at table A4 and A5. Do I want table A4 or A5? Last time I was given a constant pressure. This time I'm given a constant temperature. So if I look at table A4, here's where I'm having my temperature in the first column, and it's based on this temperature here. And so I'm going to be using table A4 with at 50 degrees Celsius. All right, I'm asked to determine pressure and volume. So I'm going to go to table A4 and find as much as I can that's related to pressure and volume from this table A4, try to figure out what I'm even looking for, what I'm doing. So at my saturation pressure at 50 degrees Celsius, which is just go to 50 degrees and then look at the corresponding pressure. This is 12.352 kilopascal. So at this pressure, at this temperature of 50 degrees Celsius, this is my corresponding saturation pressure. And then I also have information about pressure and then also about volume. So my specific volume at this temperature for my saturated liquid is 0.001012 cubic meter per kilogram. And my saturated vapor specific volume is going to be 12.026 cubic meter per kilogram. And that's pretty much all the pressure and volume information that I can find out from this problem. So I have a rigid tank that contains 3 kilograms of water at 50 degrees Celsius. This much is liquid, this much is vapor. So I have some that's liquid, some that's vapor. So I'm at this saturation pressure. So I know that my pressure for part A for pressure is this saturation pressure because I have some vapor that's occurring, I have some liquid that's occurring, I'm at that saturation pressure. That's like the definition of saturation pressure. So I have part A really easy. I just had to look it up in the table. And then part B, I'm looking for volume. So I'm going to need to do the same thing that I did before, where I want to have my volume is equal to my mass times my change in my saturated liquid vapor specific volume. But what mass do I use? Do I use 3 kilograms or do I use 1.2 kilograms? Or do I use 1.8, which would be the difference between those? I don't really know what mass to use. So one of the things that you could do is use both of the masses. So we know that our total volume is the volume of our liquid plus the volume of our gas. Just like yes, Lena, so it can involve quality. The first way I'm going to work, it doesn't involve quality, but the second way does. So I know, remember I told you before, total mass is the mass of the liquid plus the mass of the vapor, and this applies to a lot of the other concepts such as internal energy, enthalpy, and specific volume. So here it applies just normally, right? So the volume total is the volume of your liquid plus the volume of your gas. This is like a little bit of a duh concept, and these are total volumes here. So if we have specific volume, we need to include a mass term. So the mass of our liquid times the specific volume of our liquid, saturated liquid, plus the mass of our vapor times the specific volume of our vapor. This is all the same equation. So fortunately, we have the mass of our liquid and we have the mass of our vapor that we can determine because we know total mass. And then we were able to look up both of these terms. So we're able to plug and chug in this equation where we have 1.2 kilograms of water, liquid water, times by the specific volume for our saturated liquid, which is 0.001012 cubic meter per kilogram. And then plus our mass for our vapor, which we know our total mass is 3. We know the part of the water is 1.2. So the rest of it has to be vapor, which is 1.8 kilograms. And then this is going to be multiplied by 12, our specific volume here for vapor, 12.026 cubic meter per kilogram. Checking the units, we're going to be left with units of cubic meter. We're going to add those to units of cubic meter. That works. That's volume, total volume. So plugging and chugging, this gets to be 21.65 cubic meters is the size of the tank. So we could also work this problem in a different way. We could use quality. We have enough information to be able to do that. So I will show you how to do that. Does anyone need more time writing? All right. So I'm just going to clear this way here so we still have all the information. So that's one way of working the problem. The other way of working the problem is to use quality, where we know that our specific volume on average, so the average specific volume of our tank, but it's a rigid tank, so that's going to just be our specific volume of our tank, is equal to the specific volume of our liquid plus quality times the specific volume of our liquid vapor. And we know that our specific volume of our liquid vapor, there's so much freaking nomenclature in this chapter, is going to be equal to the specific volume of our vapor minus the specific volume of our liquid. So the specific volume of our liquid plus quality times the specific volume of our vapor minus the specific volume of our liquid. And in order for us to do this problem, we should first look at what our quality is. So our quality is our mass of our vapor over our mass total. So our mass of our vapor is equal to 1.8 kilograms, and our mass total is 3 kilograms. So our quality is 0.6. So now we know quality. We were able to look up these values. We have everything we need. We can plug and chug. So the specific volume of our saturated liquid is 0.001012 cubic meter per kilogram, plus our quality, which is 0.6, times our change in specific volume in the saturated liquid vapor region, which is going to be 12.026 minus 0.001012 cubic meter per kilogram. And now we're going to be adding cubic meter per kilogram to cubic meter per kilogram, which will give us a specific volume term. That makes sense. So solving this out, we get 7.2 cubic meter per kilogram. But this is only for our specific volume, not our total volume. So we need to use the equation we used before, where our total volume is mass times our specific volume. Here, our specific volume is for the entire tank, so we could use the mass for the entire tank. So we have 3 kilograms times 7.2 cubic meter per kilogram. This gives us units of cubic meter. That's what we want. We get 21.7 cubic meters. So pretty much the exact as if we had worked it the other way as well. All right. Are there any questions about anything? Yeah, Kat. The tables take a lot of practice. So we're going to be working on this for about 2 weeks, kind of building in new concepts, but they can be tricky at first. That's why I try to provide a lot of practice problems. All right. Anybody need more time writing? All right, so for the last 15 minutes of class, I want you guys to work on one for yourself. So here we have a rigid tank. A rigid tank contains 50 kilograms of saturated liquid, water. A rigid tank contains 50 kilograms of saturated liquid water. at 90 degrees Celsius. Determine the pressure and volume of the tank. So please work on this for the next few minutes. Type your answers into the chat once you get answers. Let me know if there's any questions. I'll go over it in the last few minutes of class. And yeah, just let me know. Make sure to type your answer in the chat so I can gauge how many people are still working or done or struggling with the problem. So is everyone still working, or is anybody just kind of confused and not able to go? Has anybody gotten a problem and just not typed in the chat? Like where is everybody? I'm trying to gauge if I should just go over it or if I should give you more time. So why don't you type in the chat if you would like more time or if you would like for me to go over it? Which of those? Okay, more time. Okay, well then I'll give a few more minutes for people. So just make sure to type in the chat when you get an answer, so I can know that people are done. All right, so I see that several people have gotten the problem, and we also have about 5 minutes left before I end class. So I'm just going to go over it quickly. So part one, is this a compressed liquid, saturated liquid, superheated? I'm sorry, saturated liquid vapor, saturated vapor, or superheated vapor? So it is a saturated liquid. We are told in the statement here, saturated liquid water. Later down the line, we're not going to be told it so directly. You're going to have to figure it out, but we'll do that a little later. Right now, it's still easy. We are a saturated liquid. So we are using, and we're water. So we're using table A4 or A5. And we know that we are given a constant temperature. So we are going to be using table A4. So then we can go to the tables, figure out what values we want. For part A, we're looking at pressure. So this is easy. We have a saturated liquid. We're interested in saturated pressure, and we are given the temperature. So we just go to the temperature at 90 degrees C, and we get on page 94, we're looking at table A4. I'm going to go down to 90 degrees, and the associated saturated pressure at 90 degrees is going to be 70.18 kilopascal. So I think, Kat, you meant 70.2, and that's right. So 70.18 kilopascal is going to be our saturation pressure. And we know that this is the pressure that's occurring in this tank because this is saturated liquid. Then for part two, part B, whatever you want to call it, you don't even have to label it. We're looking at the total volume of the tank. So we know total volume is going to be equal to either the mass of our vapor times the specific volume of our vapor plus the mass of our liquid times the specific volume of our liquid, or it's going to be equal to our mass total times our specific volume of our total system. So average total, you don't even really need to use it to mark anything to demark this here, but our specific volume of our whole system. So for this one, we're not told anything about a vapor. We aren't really told anything about a vapor that's occurring. We're told that this is only saturated liquid water. So we don't really even have this vapor term. So now our equations are pretty much the exact same thing. So our total volume is going to equal our mass times our specific volume. And we're only looking at specific vapor, specific specific volume of a saturated liquid, which is our sub F here. And our mass is going to be for our liquid, which is also the mass of our whole tank. This is just a T for total, but you don't have to put anything. It's just mass. So now we have our mass total is 50 kilograms. 50 kilograms. And our specific volume of our saturated liquid on table A4 at 90 degrees, it's the third column over, it is 0.001036 cubic meter per kilogram. Yeah, so this is a T for total. But you can also just put nothing, right? So you can also just put mass times specific volume. I was just trying to change it from here, right? Because we know our total is these masses added together. And then multiplying these out, you get 0.0518 cubic meter.
That's what we do for all the saturated liquids when we're not given VG.
Say that again?
Is this what we're going to do for all of them when we're not given VG? It's just liquid?
If you know that there is no saturated vapor. So this one we're told there's 50 kilograms of saturated liquid water. So we're told that the entire mass of the rigid tank is saturated liquid water. Sometimes you'll only be given a rigid tank contains 50 kilograms of saturated liquid vapor, 1.2 kilograms is water, whatever. And so then you can't do this mass total here in the same way because right now our entire specific volume is from this saturated liquid water. But if we had some vapor in here, we couldn't use this specific volume.
Okay.
Okay, other questions? All right, well, this is all for today. We're going to keep going on Wednesday with chapter 3, learning more. It's an exciting time. So make sure that you're reading and going over the definitions for chapter 3. As you can tell, there's a lot of definitions. So I will upload this recording and